Hello again, everybody. Machado back once again for more in the wonderful world of graphing quadratics. What we're going to be looking at today is going to be transformations of quadratic functions. Now, with quadratics, we looked at last time how to graph them. And as we're graphing, it can sometimes be a little tedious, right? If we make a table, we have to plug things in over and over again. If we graph using the properties, we get a lot of information, but sometimes it would be nice to just get a general idea as to what this function is going to look like and where it is. So that's what we're going to look at today. We're going to look at something called graphing form and see what we can come up with and see if we can find ways to make this a little bit easier for us. So the first thing that we're going to do is we're going to look at what happens if I just graph plain old x squared. What does that function look like? Where is it? And what can we do with this function? X squared is something that we would call a parent function. It's a parent function because it's the most basic quadratic function that we can make. We can make more complicated quadratic functions, but this is the simplest form that we can have it in. And if I was to make a table for this, it would look something like this. This isn't going to be perfect because I'm not on my graph paper yet. I probably should have done that, but oh well. I'll switch to my graph paper here in a minute. But the first thing that I'm looking at, oh yeah, that does not look good at all. Here, move this one out a little bit. I've got to start using graph paper for all of them. I'll do graph paper for the rest of the day. But this basic function is just a quadratic function, right? It's just a nice parabola. Notice where the vertex is. The vertex is that bottom piece right there, and it's right there in the middle, 0, 0. So the first thing that we're going to look at is what happens if we just add or subtract something to it. So let's start off and let's look at what happens if I have maybe f of x is equal to x squared plus 2. So if I graph this, if I was to make a table or graph it using its properties, properties aren't very helpful with one like this because really this is the only piece of information I'd get. I would still need to plug some points in to be able to see what this really looked like. So this is going to go up on either side. And notice, it's up 2 units from where it started. The original parent function started right here at 0, 0. Now my vertex is up 2. Do we maybe see a connection between where my vertex is and this plus 2? The next one, I'm going to say, what happens if we subtract 3? What happens if I subtract 3 with this function? It's going to go down 1, 2, 3. I wonder if there's a connection there. If I add or subtract a number just to my parent function, it's called a vertical shift. Vertical shift. It's going to move my function up or down from its original place based on whatever that number is that's been added. Now, we don't just have vertical shifts, we also have horizontal shifts, and we're going to look and see how those work. If I've got this one, let's go with an x plus 2 squared. Notice where that plus 2 is this time. Initially, when we looked at it here, it was after my x squared. Now, it's like it's inside of my x squared. It's inside of that function. And when it happens to be inside there, here's my ruler, it does something a little bit different. When it's inside of my function, the shift is actually going to go the opposite direction. Even though it's a plus 2, my vertex ends up being right over here, and then my function still has that same shape that it did before. But my horizontal shifts, these are the ones that tend to be a little bit harder to remember because they work backwards from what we would imagine. It's actually going to shift it this way. Not quite like what we'd pictured. Actually, if I'm adding, it's going to be shifting it backwards. So adding shifted it to the left. That's not an L. There we go. And if I was to look at the function f of x is, I've got x minus 3 squared. Once again, it's inside of there. then it's going to shift it the other direction. Even though it's a minus 3, and when we think negative and we're on our x-axis, if I've got that negative sign, I tend to think I want to move it that way, but because it's inside here, this negative 3 is actually going to be going the opposite direction. And it's going to move my function this way. I can go up. Get my picture here. So this one is going to shift it right. So these ones, those up here were vertical shifts, these ones here are horizontal shifts. And make yourself a big note that these ones right here are backwards. They are backwards from the way that you would imagine that they're going to be. So if it's a +2 here, that means it's going to the left 2. If it's a -3 here, it's going to the right 3. Okay. So if I have a couple of these combined, grab another piece of paper. If I have something like f of x is equal to an x minus 2 squared plus 3, this function is going to look a little bit different than that regular parent function, right? My regular parent function, I'm going to put that on here first so that we can see how this is going to get moved. It's going to start off, this is my regular x squared. Get that on here. Ooh, I did a good job there. And then this one goes up too. This is my plain old f of x is x squared. Now with this one, it's going to move it, this is a -2, but remember it's inside, so it's going to be opposite. It's going to move it this way 2 units, and then because I've got plus, it's going to go up 3 units. So my vertex is going to go over 2 and then up 3. And then all of these other points are going to go over 2, up 3, over 2, up 3. So my entire function gets shifted over and up. So we can have multiple transformations at once. Okay. So looking at how those change my function, the next thing that we have to look at is what does that a really do to our function? So if I've got f of x is equal to x squared, let me get that on there again. I want to look at that parent function first so that I can see what the rest of them are going to do. We already know if the number that's in front of my x squared, if it's positive or negative, that determines if it's going to go up or down. But we haven't really talked about what happens if it's a number. What happens if maybe it's a 2x squared, or maybe it's a 1/2 x squared, and what that does to the shape of my parabola. So here's my plain old x squared. And we're going to look and see, we're going to call it g of x this time, and we're going to see if we can figure out what g of x is going to look like if I've got 2x squared. I'm going to do this in a colored pen so we can kind of see it a little bit better. If I make a table for this, and I'm just going to plug in just a couple points so I can get the general shape. I'm just going to go with a -1, a 0, and a 1, just so we can really quickly get an idea as to what's happening. If I plug in a -1, I'm going to have 2 times -1 squared. Remember that negative's inside there. So I end up with a 2. If I plug this 0 in, I just get a 0. And then if I plug in a +1 right here, I'm going to end up with a +2. So I'm going to go ahead and add those here. So here's this one. And then instead of only going up 1, I'm actually way up here. And then I'm going to be way up here. Let's plug in one more point so we can kind of see what happens. Let's plug in a -2 and a +2. So that way I can see one point on either side so I can see where I'm going. I've got a 2 times -2 squared. So that's going to give me a +8. If I plug in a +2, I'm going to end up with a +8 again. So I've got, There's 2, 4, 6, 8. So I'm going to be right here and right here. You'll notice that the shape of this one is much skinnier. We like to call this a stretch. It's stretched out, so it's almost like you're taking it and you're stretching it up. You're pulling it and making it skinnier. So it's skinny or stretched. Now, where'd my other colored pen go? Hold on. Here we go. With this purple one here. Then, if I've got maybe h of x is, let's look at maybe 1/3 times x squared. If I make my table again, I'll just go ahead and go from -2 to +2. Plugging these points in, we'll see what happens. The easiest one to plug in this case is a 0. I just end up with 1/3, or no, sorry, 0. If I plug in a 1, I get a 1/3, and then same thing here, I'm going to get a 1/3. If I plug in a 2, that's the one that takes a little bit more thinking. So 1/3 times a -2 squared. That's going to be a 4, and then a 3. That's a 4/3, and then 4/3. So if I'm going to plot these points, for -2, I'm up 4/3. That's only right about here. And then if I'm at a -1, I'm down here at 1/3. And then I have that same vertex. I haven't moved, right? I'm not adding or subtracting anything. As you notice, this is making it super squished. It's like we took that parent function and we just went shh, and we squished it down. So we call this a squish. Sometimes we also like to think of it as being kind of like a fat parabola, right? It holds a whole lot more, kind of like a really big cup or something. Okay. So let's see what these can look like if I just have all of it into one, and see if it can make our graphing a little bit easier for us. Okay. So let's look at, if I've got the function, we'll go with f of x is, let's say I've got a -2 times x plus 4 squared minus 3. Oops, sorry. Did not know you couldn't see that. All right, so I'm going to go ahead and see first if I can figure out where my vertex is going to be. That's going to be my very first step. So if I'm looking at this right here is telling me it's going to, remember, if it's positive, it's actually going the opposite direction, so it's going to go that way. I'm going to go left 4 and then down 3. Right? This right here tells me down 3. This piece right here tells me left 4. So I'm going to go from here, I'm going to go down 3 and then to the left 1, 2, 3, 4. So this is the new place of my vertex. The next thing that I want to look at is this going to open up or down? And in this case, it is going to open down. Then if I just want to get a general shape for this function, what I can do is this one right here, it's going to be skinny because I've got a multiplier of 2. Okay? So because it's skinnier than a regular quadratic, we're going to be going down at twice the rate. And when we're graphing using the transformations, we don't necessarily care all that much about the whole shape of it. We're just going to try to get a general idea. So let's look at another one. Let's look at g of x is 1/2. And let's go with x plus 2 squared. And then let's go with a plus 1 just to see what happens there. Once again, we're going to start by trying to figure out where our vertex is. The parent function is that x squared, so I know I'm going to be starting at the middle and then I'm going to move. This is a positive, right? So we're still going to go back 2, just like we did last time, but this time we're going to go up 1. This tells me that it's going to open up, and I know that it's going to be squished. It's like it's going to be squished down and it's going to get fatter. So instead of going at the normal rate, it's going to go something like this. And remember, graphing using these transformations, we're just trying to get a general shape. Now, it could be really helpful, but not always are we given the function in this form. Sometimes we are, but not always. Sometimes it's in a form like what we're used to seeing, standard form. So if we're given a function that looks like this, f of x is equal to x squared plus 6x plus 5, but we need to get it into that graphing form. We want to be able to get it into that form where I've got my vertex easily identified and my A factored out if I can. So if I'm looking at this piece right here, basically what I want to turn it into is an x minus h squared plus k. This is called vertex form, or graphing form, depending on the book or problems that you're looking at. And all that it tells me is that my vertex is hk. And that's why this is a minus, because remember, we're going the opposite direction of whatever this is. So this one here ends up being a minus. So this piece right here, what I need to figure out is how to get it from this form into this form. And if I'm taking something that's not a perfect square and I'm turning it into a perfect square, what we're going to do is we're going to look at it like we're completing the square. If you remember from last week. So with completing the square, the part that we're going to be looking at, if we remember, we're going to be looking for that b over 2 and then squared to be able to figure out what to add. So I'm going to rewrite this just a little bit so I have a little bit more space. I want to add something to this because I want to be able to turn this into something squared plus something. That 5 isn't going to be helpful, so I'm just going to make that go over to the side. But because it's an equation, I can't just add something and not change it on both sides. But because I've got my function here, I can't just add it over here. But what I can do is if I add something on one side, I can also subtract it. If I add 2 and subtract 2 at the same time, I haven't actually changed my equation. It's like I'm adding in a 0. Right? If I add in this case, I'm going to have 6 divided by 2 and then squared. That's going to give me 9. If I add a 9 here, but then I take it away again, I haven't actually changed my function at all. It's the same function. I'm just rewriting it in a different form. So I'm completing the square here, and whatever I've added, I'm going to go ahead and subtract it away. So now, my f of x is going to be, this is that perfect square. Remember, we're engineering it to become a perfect square. And then over here, it's going to be actually not even plus anymore. Positive 5 minus 9 gives me a negative 4. So now I have it in that graphing form. I know that my vertex is at negative 3, negative 4. And if I wanted to, I could graph that real quick. I'm going to go ahead, just do a quick sketch, not even on graph paper, just so that we can kind of see what this would look like. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Okay, I'm going to go back 3 and then down 4. And then it doesn't have any squish or stretch to it, so it's just going to go up and then up. Okay, remember, if we're just doing the transformations, we're looking at it in terms of a really basic function. We're just trying to see where is it and kind of sort of what does it look like. If I really wanted to know more about this, I would want you to graph it using the properties. But if we're just using transformations, we're just trying to get a general shape or a general idea as to where this is. Let's look at another example of that. If I have this function, I've got negative x squared minus 4x plus 2. So for this one, what I can do is I can still try to complete that square, but this one's going to be a little bit different because in order to complete the square, remember the way that we've looked at it, our a has to be a 1. So for these terms here, I'm actually going to factor out a negative 1. Right, I'm going to leave this 2 by itself, and I'm taking these two terms right here, and take out that negative so that I can deal with just these pieces that are inside. Now I'm going to take this. I've got 4 divided by 2, and then squared gives me a 4. So I'm going to add 4, but I have to remember if there's something outside here, it's really like I didn't really add 4, I added a negative 4. So if I add a negative 4, then I have to add a positive 4 to make up for it. Oh, here, let me move this over to the side. Okay? Remember, whatever I do to the equation here, it's not like I've got both sides. I'm only on one side, so I have to, if I'm adding a negative 4, then I have to add a positive 4 to get rid of it. So I'm going to have a negative, this is going to be an x plus 2 squared plus 6. If I graph this real quick, I can easily identify where my vertex is and then go from there. So in this case, my vertex is going to be at a negative 2 and then a positive 6. So I'm going to go back 1, 2, and then up 1, 2, 3, 4, 5, 6. So my vertex is right about here. Now with this one, it's going to open down, so it's going to go down like this. Okay. So that gives me a real quick idea as to where my function is, what it looks like, and just the general shape of it. When we're dealing with transformations, they can be something that is very helpful to give you a good general idea of your function. It can help you move things around. It can also help you write equations of functions, which we will look at a few weeks from now. Okay, so once again, if you guys have any questions, you know what to do. Email me. If we need to, we can set up a video chat or something like that to make sure that you're getting what you need. Have a wonderful day.